Welcome to the cosmic frontier, where the James Webb Space Telescope, JWST, is reshaping our understanding of the universe. In today's episode, we're diving into the latest groundbreaking discovery by the JWST that's causing a stir in the world of cosmology. Fasten your seatbelts as we embark on an astronomical journey that challenges the very fabric of our cosmic knowledge. Something is amiss in the ever-expanding cosmos. Nearly a century ago, astronomer Edwin Hubble made a groundbreaking discovery. The universe was expanding like an inflating balloon, with galaxies rushing away from each other. Tracing this expansion back in time led to our prevailing theory of the universe's inception, the Big Bang. However, over the past decade, a troubling inconsistency has emerged. The rate of the universe's expansion, known as the Hubble constant, seems to vary depending on where astronomers look. This discrepancy has deepened, especially following more than 2 years of observations by the James Webb Space Telescope. These precise new observations have starkly highlighted the issue, potentially challenging the standard model of cosmology. Adam Ree, a professor of astronomy at Johns Hopkins University and leader of the team responsible for these new measurements, points out the significance of this disagreement. It raises fundamental questions about our understanding of the universe's composition and its physical laws. Despite differing views, many cosmologists concur on one aspect: the universe's journey began with a monumental bang. From there, a young, rapidly expanding plasma cosmos took shape, setting the stage for the universe as we know it. In the early universe, a tumultuous mix of matter and antimatter particles emerged, immediately annihilating each other upon contact. In this plasma quagmire, matter and antimatter should have completely obliterated each other. However, scientists theorized that an unexplained imbalance led to the production of more matter than antimatter, preventing the universe's instant collapse. The force of gravity played a pivotal role, compressing these plasma pockets and intensifying their heat. This environment facilitated the propagation of sound waves, known as baryon acoustic oscillations, which moved at over half the speed of light across the plasma's surface. Additionally, the dense energy of the universe's early contents warped space-time, extricating a portion of matter from destruction. As the universe expanded, akin to a balloon, normal matter, which interacts with light, started clustering around invisible dark matter, forming the earliest galaxies. These galaxies were linked by a vast cosmic web. Initially, as the universe spread, its energy density and consequently its expansion rate diminished. However, about 5 billion years ago, a shift occurred. Galaxies began to drift apart again, this time at an accelerating pace, heralding another chapter in the cosmic narrative. An enigmatic and unseen force, known as dark energy, is a fundamental concept in cosmology. The most prevalent and straightforward theory posits that dark energy is a cosmological constant, a uniform, inflationary energy that permeates all of space and time. This concept, integrated into the fabric of spacetime, was denoted as lambda by Einstein in his theory of general relativity. As the cosmos expanded, the density of ordinary matter lessened, while the density of dark energy remained constant. This shift gradually elevated dark energy's role as the primary driver of the universe's expansion. The cumulative energy densities of ordinary matter, dark energy, and light determine the maximum rate at which the universe can expand. These components are crucial in the lambda cold dark matter (CDM) model of cosmology, which charts the universe's evolution and foresees its eventual fate, a big freeze or heat death, where matter disperses to the point of extreme dilution. The CDM model has successfully predicted numerous cosmic phenomena. However, a significant issue looms. Despite extensive research, astronomers remain baffled about the true nature of dark matter and dark energy. Ofer Leav, a professor of astronomy at University College London and a participant in galaxy surveys, highlights this knowledge gap in the field. Dark energy is a pivotal yet perplexing element in our understanding of the universe. It's widely accepted that the universe's current composition is approximately 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The challenge, however, lies in our limited understanding of the latter two components. Compounding this issue is a significant threat to the lambda cold dark matter (CDM) model, a phenomenon known as the Hubble tension. This refers to the differing expansion rates of the universe observed through various astrophysical methods. Techniques that probe the early universe indicate a faster expansion rate than what the CDM model predicts. These methods have undergone rigorous validation and numerous observations, leading to the conclusion, as stated by Ree, that the discrepancy could mean our current model might be missing key elements. Measuring the universe's expansion involves more complex methods than simple radar detection. One approach examines the cosmic microwave background, CMB, the residual glow from the universe's infancy, just 380,000 years after the Big Bang. Visible across the entire sky, this relic was meticulously mapped to determine the Hubble constant with less than 1% uncertainty. This mapping was achieved by the European Space Agency's Planck satellite, which operated from 2009. Between 2009 and 2013, the Planck satellite gave us a unique view of the universe's early stages, often referred to as the cosmic baby picture. In this nearly uniform image of the young universe, variations in temperature, indicating areas of different densities, marked the beginnings of cosmic structure. These variations, shaped by baryon acoustic oscillations, were the precursors to the cosmic web, a vast network of intersecting strands that would later foster the birth of galaxies. By studying these early ripples, cosmologists using the Planck satellite were able to estimate the amounts of regular matter, dark matter, and the cosmological constant, or dark energy. Integrating these values into the standard model yielded a Hubble constant of approximately 67 kilometers per second per megaparsec. To put this in perspective, a megaparsec is about 3.26 million light-years. This means that a galaxy 1 megaparsec away from Earth is moving away at 67 km/s. At 20 megaparsecs, this rate increases to 1340 km/s, and it continues to rise exponentially from there. At distances beyond 4,475 megaparsecs, galaxies recede faster than the speed of light. Another method used to determine the universe's expansion rate involves observing pulsating stars known as Cepheid variables. Cepheid variables are a type of dying stars characterized by outer layers of helium gas that expand and contract. This pulsation occurs as they alternately absorb and release the star's radiation, causing them to flicker periodically, much like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt made a groundbreaking discovery. The intrinsic brightness of a Cepheid variable was directly related to the frequency of its flicker. The brighter the star, the slower it flickered. This insight allowed astronomers to measure a star's absolute brightness and thus determine its distance, revolutionizing the use of Cepheids as cosmic standard candles for gauging the vast scale of the universe. Astronomers utilize these pulsating Cepheids to build what is known as a cosmic distance ladder. Each rung of this ladder represents a step back in time, allowing astronomers to piece together the universe's expansive history. This method is among the most accurate for measuring cosmic distances. According to Wendy Friedman, an astrophysicist at the University of Chicago, constructing a cosmic distance ladder involves a meticulous process. The first rung is established by selecting nearby Cepheids and corroborating their distances, as measured by their pulsating light, with geometric data. Subsequent rungs are added using observations from further Cepheids. Astronomers then examine the distances of stars and supernovas on each rung, comparing how their light has been redshifted to infer distance and movement. As the universe expands, the wavelengths of light stretch, shifting to longer, redder wavelengths. This phenomenon provides a precise way to measure the Hubble constant. In 2019, a notable application of this method was led by Rees and his team using the Hubble Space Telescope. They focused on one of the Milky Way's nearest neighbors, the Large Magellanic Cloud. The result they obtained was startling. They measured an expansion rate of 74 kilometers per second per megaparsec, significantly higher than the rate determined by the Planck measurements. However, the Hubble Space Telescope's precision was limited, especially in observing crowded regions of space. This limitation often caused distant Cepheid variables to blur with nearby stars, leading to potential measurement errors. This left some room for skepticism among cosmologists, who argued that the surprisingly high rate could be due to these inaccuracies. The launch of the James Webb Space Telescope in December 2021 offered a new opportunity to either resolve or confirm this discrepancy. With a mirror 6.5 meters wide, nearly 3 times larger than Hubble's 2.4-meter mirror, James Webb can detect objects 100 times fainter than Hubble and has enhanced sensitivity in the infrared spectrum. This allows it to observe a broader range of wavelengths. By comparing Cepheid variables observed by James Webb in the galaxy NGC 4258 with observations of bright-type Ia supernovas, astronomers hoped to refine their measurements of the universe's expansion rate. Type Ia supernovas serve as another type of standard candle in cosmology due to their consistent absolute luminosity in distant galaxies. Using these supernovas, Rees and his colleagues achieved a nearly identical result to their previous findings, an expansion rate of 73 kilometers per second per megaparsec. This finding aligned closely with other measurements, including one by Friedman using the Hubble Space Telescope that focused on the rapid brightening of red giant stars at the most luminous tip of their branch, and another study that utilized the gravitational bending of light by massive galaxies, yielding results of 69.6 and 66.6 chem/s per megaparsec, respectively. A separate assessment, also based on the bending of light, returned a similar value of 73 chem/s per megaparsec. These varying yet closely clustered results left cosmologists grappling with their implications. Ryan Keeley, a cosmologist at the University of California, Merced, who has been investigating the Hubble tension, noted the significance of these findings. The cosmic microwave background, CMB temperature, is measured with about 1% precision, and the Cepheid distance ladder method is nearing similar accuracy. Therefore, a discrepancy of 7 chem/s, although seemingly small, is highly unlikely to be due to random chance. This discrepancy indicates a definite phenomenon that requires explanation. These new results have broadened the scope of possible explanations, causing cosmologists to diverge into factions, each pursuing vastly different theories to resolve the Hubble tension following observations by the Hubble Space Telescope. The ongoing attempt to resolve the Hubble tension reached a critical point at a 2019 conference held at the Kavli Institute for Theoretical Physics, KITP, in California. The situation, as described by David Gross, former director of KITP and Nobel laureate, escalated from a mere tension or problem to a crisis. However, finding a solution remained elusive. Rees, in response, is exploring a modification to the lambda cold dark matter (CDM) model. His approach suggests that dark energy might not be a constant force, but could evolve throughout the universe's history, influenced by yet unknown physics. Contrasting this, Ryan Keeley's research supports the current CDM model, showing that the expansion rates align with its predictions right back to the cosmic microwave background, CMB. Therefore, if any amendments are needed, they would likely pertain to the very early universe. One possibility involves introducing additional dark energy prior to the CMB's emergence, boosting the universe's expansion without fundamentally deviating from the standard model. Meanwhile, another group of astronomers, considering both the Hubble tension and the observation that the Milky Way is situated in a massive supervoid, argue that both the CD model and our current understanding of dark matter might need a complete overhaul. The question of what could replace these prevailing theories remains a subject of intense debate and research in the astronomical community. Pavel Krupa, a professor of astrophysics at the University of Bonn, advocates for a theory known as modified Newtonian dynamics, MOND. This theory suggests that at extremely weak gravitational forces, about 10 trillion times weaker than those on Earth's surface, such as the forces between distant galaxies instead, MOND proposes that different equations are needed to explain these gravitational interactions. While some astronomers have contested the claims of MOND, Krupa argues that attempts to adjust the standard cosmological model are only adding complexity to an already intricate theory. He sees the current challenges in cosmology as a fundamental breakdown of existing scientific frameworks. However, there's a more optimistic perspective. It's possible that the standard model only requires minor adjustments. Krupa compares the current situation with dark matter and dark energy to the ancient Greek concept of epicycles, small circular motions that were used to explain planetary orbits around Earth. These models were highly accurate for their time, but the understanding evolved significantly when astronomers later placed the Sun at the center of the solar system. This analogy suggests that our current theories, while fitting existing data well, might need a paradigm shift to fully comprehend the universe's mysteries. As with the gradual obsolescence of epicycles and older models of the universe, current theories about dark matter and dark energy might also evolve or become irrelevant. This is a philosophical consideration, but it's also possible that dark matter and dark energy exist and simply haven't been discovered yet. Projects like the CMBS-4 at the South Pole and the Simons Observatory in Chile are delving into ultra-precise measurements of the early universe's radiation to uncover clues. Additionally, efforts are being made to analyze the dark matter maps that will be produced by the European Space Agency's Euclid Space Telescope, as well as the future Dark Energy Survey by the Dark Energy Spectroscopic Instrument. While it may seem less probable now, it's also still conceivable that the Hubble tension could be resolved by identifying some overlooked systematic error in current measurements. Scientists like Friedman are optimistic about the potential revelations from the James Webb Space Telescope. Her team is utilizing the telescope's advanced capabilities to make ultra-detailed measurements of Cepheid variables, the tips of the red giant branch stars, and a specific type of carbon star known as JAGB stars. Once the necessary data is gathered, it will be intriguing to see how these various measurements align and what new insights they might provide. This exploration aims to provide a comprehensive, systematic answer to some of the universe's mysteries. The James Webb Space Telescope might one day resolve a long-standing debate in the astronomical community, and many are hopeful that this day will arrive soon. While scientists and astronomers have amassed considerable knowledge about the universe, there is still a vast expanse of uncharted territory. The universe is filled with unsolved mysteries that continue to captivate the world's leading astronomical minds. Among the 21st century's most pressing astronomical questions, the James Webb Telescope is expected to provide insights into the mysteries of our expansive universe. One such mystery involves the merging of supermassive black holes. When black holes collide, they create gravitational waves that ripple through space. Thus far, observed mergers have primarily involved stellar mass black holes, which are relatively small compared to supermassive black holes. These colossal black holes, with masses reaching billions of solar masses, are found at the center of most major galaxies. When galaxies collide, it raises the question of what happens to the supermassive black holes at their cores. The logical assumption is that they would merge as well. However, there is a complication in understanding the dynamics of such colossal interactions, and this is where the James Webb Telescope's observations could be crucial in advancing our understanding. For supermassive black holes to spiral inwards and merge, they need to shed energy, which they typically do by transferring heat to the surrounding gas, dust, and stars. However, when these black holes come within about a parsec of each other, they encounter the final parsec problem. At this close proximity, there's insufficient material around them to continue losing energy effectively. This issue suggests that the supermassive black holes should remain in orbit around each other indefinitely, without merging. Yet, intriguingly, recent findings from the nanograv experiment indicate that the universe may be filled with gravitational waves stemming from supermassive black hole mergers. The subtle signals captured in this data could provide astronomers with the necessary clues to unravel this conundrum. Another fascinating question concerns the actual appearance of the universe. When we examine the large-scale structure of the universe today, we see countless galaxies arrayed along seemingly endless filaments, creating a cosmic web. This structure is thought to have originated from minute density variations in the very early universe. These variations acted as seeds for the eventual development of this cosmic structure. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q and a sessions with experts. Your membership will grant you the chance to participate in live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.